Okay, so this is problem 11 from chapter 3. We have a 2.4 amp current source, and over here we have 20 ohms in series with 10 ohm resistor. Over here we have 6 in parallel with 90 and 10. And we need to find the voltage drop across the 20 ohm resistor and the current that goes through the 90 ohm resistor. And the goal of this problem falls under section 3.3 and 3.4. So we want to use tools that show an understanding of the voltage divider circuit, and or in this case I'm going to use the current divider circuit to solve this problem. So remember, current division says that the current will split such that you take Req, the equivalent resistance, over the resistor that you want, the Rj, and that's how the current will divide. So that's the skill we're practicing today. So let's get started. The first thing you want to do is you want to simplify this circuit and find the equivalent resistance so that we know how will the current, this 2.4 amp resistor, how will it split? How much will go here, how much will go here? That means we have to find this branch and this branch and then apply current division to that. So let's get started. Here's our 2.4 amp. Over here we have 30 ohms, and over here we have to figure it out. We've got 6 in series with 90, which is in parallel with 10. And so what that's going to equal is 6 plus 1 over 90 plus 1 over 10 inverse. And when you do that, you should get, okay, first I'm going to do the parallel branch. 1 over 90 plus 1 divided by 10 inverse, and then plus 6 to that, it gives me 15. So over here, my equivalent resistance is 15. At this point, you can probably use common sense to figure out how things will divide, right? There is less resistance here, so, well actually rather than use common sense, because on a test you might not see that. So what you want to do is just apply current division, which says the equivalent resistance, which we just calculated to, well, we need to calculate that first. We need 30 in parallel with 15, and that's going to be 1 over 30 plus 1 over 15 inverse. 1 divided by 30 plus 1 divided by 15. My equivalent resistance is 10, and on an exam you just want to do a quick reality check or spot check. You have 10 for equivalent resistance is less than either one of those, so that's a pretty good indication that you didn't make any calculator mistakes. So now we just simply apply current division, and current division says that the current that will go here, I-30, we'll call that, and the current that will go here, I-15, is going to split such that I-30 is going to be, take the current, the equivalent resistance, which is 10 in this case, over what we're looking for. We're looking for the branch through there, 30, and then we're going to multiply that by 2.4, the total, the current that's going into the node and splitting. So 2.4 times 10 divided by 30 gives me 0.8. Hold on. 2.4 times 10 divided by 30 gives me 0.8. So now I know that 0.8 is going this way. And at this point I could just use KCL and just subtract this and know that 1.6 is going to go in that direction. But for the sake of practicing current division, we're going to go I-15 is going to equal 10 over 15 times 2.4 amps. So 10 divided by 15 times 2.4 gives me 1.6 as expected. So we know 1.6 is going this way. Remember, current division says total resistance divided, equivalent resistance divided by the branch that you're looking for. So V naught, what is V naught? So now we have over here, we know 0.8 is going to go there. We know 1.6 will go there. Now, what is the voltage drop over there? Well, V is just going to be equal to I times R. We know 0.8 amps times 20 volts, right? So 0.8 times 20 is 16 volts. And let me just check to make sure that's what I've got before. Yes. Okay, so now V naught is 16 volts. And now, I'm going to erase all this. Now I want to find what is that current. We know 1.6 is going through here, and we'll split to two currents. Again, we apply current division to solve this problem. So that means we need to find the equivalent resistance here and divide that by the branch we're looking for. So 90 in parallel with 10 will be 1 over 90 plus 1 over 10 inverse. 1 divided by 90 plus 1 divided by 10. I get 9 ohms. It's less than both of those, so that's a good indication there aren't any calculation errors. So now we know what it is. We're going to find I naught is equal to Req divided by 90, the branch that we're looking for. And Req is 9. And the branch that's going to split there is at 1.6 amps. So it gives you 1.6 times 9 divided by 90. It gives me 0.16 amps. Okay, and that's what I got before. And now we want to know what is the power that is dissipated in the 6 ohm resistor. And power is just I squared R. So P, if you can't remember that, I always just remember P is equal to VI. I only remember two things. I remember P is equal to VI and V is equal to IR. Fewer, so V is equal to IR times I, which gives me I squared R. The I that's going through that is 1.6. And the resistor is 6 ohms. That gives me 1.6 squared times 6. I get 15.36 watts. And that's what I got before. Yes. Okay, and the last part of the problem is what is the power developed by the 2.4 current source? Well, remember in part A when we were doing current division, we had narrowed it down, our circuit down to 30 over here, right? And then over here, we had 15. So now we can see that these are parallel connected. Even though they lay on opposite sides, they are connected at two endpoints, which is by definition what a parallel connection is. So we have 15 in parallel with 30, so which is an equivalent 1 divided by 15. Remember, equivalent resistance is calculated like this: 1 over 15, 1 over 30 inverse, plus 1 divided by 30 inverse gives me 10. 10 ohms is the equivalent system of the equivalent resistance of the entire circuit. And P, the power created by the, developed by the 2.4 amp, is just IR, I squared R, which gives me 2.4 amps squared times 10 ohms. And that is 2.4 squared times 10 is 57.6 watts. And that's the answer to this problem.